Imagine a cosmic dance. Stars are born. They shine brightly. Eventually, they fade away. This celestial ballet is a mesmerizing spectacle that unfolds over millions of years. Each star, with its unique journey, contributes to the grand tapestry of the universe. This process is a beautiful example of a function at work. Just as stars follow a life cycle, functions in mathematics follow a set of rules to transform inputs into outputs. The universe, in its infinite complexity, mirrors the elegance of mathematical functions. A function is like a rule. It defines a relationship between two sets of elements. In simpler terms, it tells us how to get from one point to another, much like a recipe tells us how to turn ingredients into a dish. It connects one thing to another. For instance, in a graph, a function connects each input value to a corresponding output value, creating a visual representation of the relationship. In our cosmic dance, the function connects a star's age to its brightness. As a star ages, its brightness changes in a predictable manner, much like how a function maps inputs to outputs. In mathematics, functions have a specific job. They provide a systematic way to describe how one quantity changes with respect to another. This is crucial in fields ranging from physics to economics. They take an input and transform it into an output. This transformation is governed by a specific rule or formula, ensuring consistency and predictability. Think of a vending machine. You input money. The machine processes this input according to its internal mechanism. The machine outputs a snack. This is a simple, everyday example of a function in action. The input, money, is transformed into an output, snack, based on a predefined rule. The input is called the domain. It represents all possible values that can be fed into the function. The output is the range. It encompasses all possible values that the function can produce as a result. Let's explore these concepts further. By understanding functions, we gain a powerful tool to describe and predict the world around us, from the smallest particles to the vastness of the cosmos. The domain of a function is like its appetite. It tells you what the function can eat or process. In other words, it's the set of all possible input values. The range is like the vending machine's offerings. It's the set of all possible outputs. The range depends on the function's rule and the available inputs. Understanding domain and range helps us understand the function's limitations and possibilities. Let's start with a simple function, the linear function. Imagine drawing a straight line on a graph. This line represents a linear function. Its equation might look something like this: y equals 2x plus 1. The domain of a linear function is all real numbers. Why? Because you can plug any number into the equation for x and you'll get a valid output for y. The range is also all real numbers. The line extends infinitely in both directions. Now imagine a parabola. This smooth, symmetrical curve is one of the most fundamental shapes in algebra and calculus. This elegant curve represents a quadratic function. Quadratic functions are polynomial functions of degree 2, and they always graph into a parabola. Its equation might look like this: y equals x squared minus 2x plus 1. This is the standard form of a quadratic equation, where the highest exponent of x is 2. The domain of a quadratic function is also all real numbers. This means you can substitute any real number for x, and the function will produce a corresponding y value. You can plug in any value for x. Whether it's a positive number, a negative number, or even 0, the quadratic function will always give you a result. The range, however, is a bit more interesting. Unlike the domain, which is all real numbers, the range of a quadratic function depends on the direction of the parabola. The parabola has a lowest point or a highest point if it's flipped. This point is crucial in determining the range of the function. This point is called the vertex. The vertex is either the minimum or maximum value of the quadratic function, depending on whether the parabola opens upwards or downwards. The range of a quadratic function is all the y values from the vertex up or down. If the parabola opens upwards, the range is all y values greater than or equal to the y-coordinate of the vertex. If it opens downwards, the range is all y values less than or equal to the y-coordinate of the vertex. Understanding the range helps in graphing and solving quadratic functions effectively. Section 5. Exploring absolute value functions. Imagine folding a piece of paper in half. The fold line represents the absolute value function. This function makes all inputs positive. For example, the absolute value of -3 is 3. The absolute value of 3 is also 3. The domain of the absolute value function is all real numbers. You can find the absolute value of any number. The range, however, is only positive numbers and 0. The function always outputs a non-negative value. Section 6. Navigating rational functions and their domains. In this section, we will delve into the fascinating world of rational functions and explore their domains in detail. Rational functions are like fractions. They consist of a numerator and a denominator, much like the fractions you are already familiar with. They have a numerator and a denominator. The numerator is the top part of the fraction and the denominator is the bottom part. Understanding this basic structure is crucial for working with rational functions. For example, y equals x plus 1 over x minus 2. This is a simple rational function where the numerator is x plus 1 and the denominator is x minus 2. The domain of a rational function is a bit trickier. Unlike simple polynomials, rational functions have restrictions on their domains. We need to avoid making the denominator 0. This is because division by 0 is undefined in mathematics and can lead to errors in calculations. Dividing by 0 is a cosmic no-no. It's one of the fundamental rules in mathematics that we must always remember. To find the domain, we find the values of x that make the denominator 0. This involves setting the denominator equal to 0 and solving for x. Then we exclude those values from the domain. By doing this, we ensure that the function remains valid and free from undefined points. The range of a rational function can be a bit more complex. Unlike the domain, which is determined by the denominator, the range depends on the specific function and its behavior. It depends on the specific function. To determine the range, we often need to analyze the function's behavior, including any asymptotes or holes in the graph. This can involve more advanced techniques such as calculus or graphing. By understanding both the domain and range of rational functions, we can gain a deeper insight into their behavior and how they can be applied in various mathematical contexts. Whether you're solving equations, analyzing graphs, or working on real-world problems, mastering rational functions is a valuable skill that will serve you well in your mathematical journey. Section 7. Understanding square root functions. Imagine a tree growing. Its roots spread out, but they can't grow above the ground. The square root function is similar. It has a restricted domain. You can't take the square root of a negative number in the real number system. The domain of a square root function is all the x values that make the radicand or the expression under the radical sign non-negative. The range is all non-negative y values. The square root of a number is always positive or 0.
Know you've been a good friend.
Section 8. Putting it together. Domain and range in harmony. Domain and range are like two sides of the same coin. They help us understand the behavior of functions. The domain tells us what the function can handle. The range tells us what the function can produce. By analyzing the domain and range, we gain valuable insights into the function's limitations and possibilities. Section 9. Practice makes perfect. Test your understanding. Ready to test your cosmic knowledge? Try these exercises. Find the domain and range of the following functions. 1. Y equals 3x minus 5. 2. Y equals x squared plus 4x minus 1. 3. Y equals the absolute value of x minus 2 plus 1. 4. Y equals x plus 3 divided by x squared minus 1. 5. Y equals the square root of x plus 4. Remember, practice makes perfect. Section 10. Conclusion: the power of domain and range. Domain and range are essential concepts in mathematics. They empower us to understand the language of functions. By mastering these concepts, we unlock the secrets of mathematical relationships. From the smallest particles to the largest galaxies, functions govern the cosmos. By understanding domain and range, we gain a deeper appreciation for the elegance and order of the universe.